So the first part that we're going to be understanding under D3 today is where we're going to be focusing of motion of particles, okay, in a electromagnetic field. Okay, so when we are saying electromagnetic field, there are situations where we are going to consider only in electric field, only in magnetic field, and in the combination of both. Okay, so first and foremost, we will understand that if we have an electric field, how do charged particles behave in the presence of electric field? We will see some equation that we can establish from here or we can derive it from here. So when we talk about electric field, the case that we really need to understand here is basically for parallel plates. Okay, so an electric field is created by individual charges as well, an isolated charge. But our focus is going to be only on parallel plate because an individual charge not does not really create significant change into the motion of the particles. Okay. So in parallel plates, let's say the top end is connected to a positive supply and the bottom end is connected to supply. The top end is going to be positively charged here. Okay. The bottom end is negatively charged, therefore. So we have an electric field that gets established between the positive and the negative end. Okay. So we have straight lines indicating that field is uniform. Towards the edge, we have something called as edge effect. So the field lines curve. Okay. This effect is basically known as edge effect. So knowing how to sketch these lines is also essential. Now considering the same parallel plate and considering the same position of the charges, we are considering a case where I have a negative charge here. Okay. In which direction will the negative charge? Oops, my bad. I think I drew the same charge here. This needs to be negative. Okay. Where will the negative charge therefore move? It's going to be moving upwards. Okay. Now it is moving up because the force on the charge is due to force on charge is due to electric field. Okay. So we say that the only force acting on the charge is the electric force. So the net force acting on the charge is the electric force. And therefore we say that mass into acceleration can be written as E into Q. So if you want to find the acceleration of this charge, it will be E times Q, the whole divided by mass. Okay, this is one of the kinds that we can solve. Now, in this case, at times examiners do not give us the electric field value directly, but they do tell us the fact that this is connected to a positive end and the bottom plate is connected to a negative end. This information is given to us, and the plate to plate distance is separated by distance, and the potential difference is, let's say, V. If we are aware of this particular information, then we can state that the electric field is also equal to V by T. So based on this, like if this is your equation number one, and if this is your equation number two, so we can use both these equations one and two, and we can write this as acceleration is equal to V by D into Q by M. So if you see, there are variations that are possible in these equations where we are given some set of information in a very different manner. Instead of electric field, we directly have given V and D. So we need to understand that electric field can be substituted as V by D. So awareness of this equation is important. So one of the cases, the same thing, okay, all of it of this similarly works for similarly works for the positive charge as well. Okay. Similarly works for positive charge between the plates. Any
So
questions?
can you explain the E is equal to V by D part again?
Yeah. So you understand the fact that electric field can be calculated as V by D.
Yeah.
Okay. So where in the equation of acceleration, in place of E, can I write V by D?
Oh, okay, got
We're
you.
substituting this here basically. So from 1 and 2, we get A is equal to V by D into Q by M. Okay.
Yeah, fine.
So we also have equation for electric field strength, which is force per unit charge. Okay, but that is not applicable for parallel plates. E equals to V by D is applicable for parallel plates only explicitly. Okay, so F by Q is something that we will not talk about it right now between the plates. Okay, so this is the first thing that we need to understand for electric field if the charge is already inside the field. Okay, so this is one of the types. The second thing that we need to know for electric field here is that if we have a plate here, okay, where this is, let's say, the positive end again, and we have here as the negative end, we will notice that, okay, if I have a negative charge, this negative charge, when it is launched inside the plate horizontally, the tendency of this charge is basically to move towards the positive plate. Okay, now why is that the negative charge is a tendency to move towards the positive plate? That's because there is a net force acting upwards. Okay, is it valid to state that if it moves upwards, the net force is the electric force minus the weight of the charge? Yes. So this net force will become Ma. Electric force, we can write it as Eq, and this will be minus Mg. Okay. Now there could be modifications there for electric field in terms of V by D and so on and so forth. Okay. Now this can also be the case in the situation above. Okay. But here we are talking about the case when the charge is held in the state of rest and released. Okay. So here we are not taking weight into account, but you can take weight into account. Then your net force is basically going to just change as electric force minus weight, just like the way we had it over here. Okay. Now this also leads to a case of projectile motion. So if you see, this is like a horizontally launched projectile. Horizontally launched projectile. Okay. So if I want to find where exactly on the plate does it land, so I might want to find the horizontal distance. Okay. Where this over here is, let's say, the vertical distance, which is d by 2. And I might have to find out s of x, where this is horizontally launched. Okay. So very, very good topic to correlate with electricity and unit on mechanics and kinematics. So just have the awareness of this. The next thing that we will move on to is understanding that how does motion of a charge happen in the presence of magnetic field. Okay. So the underlying principle or the statement here is that a moving charge, okay, a moving charge in the presence of in the presence of magnetic field, presence of magnetic field experiences a magnetic force. Okay. If you see this statement here, very, very important is that the charge must be moving. That's the first important thing. Okay. And when we say it's in the presence of magnetic field, presence mean it has to cut the magnetic field. That is very important here to understand. Okay. So if I state the fact that I have a situation where I have magnetic field pointing into the page, let's say. Okay. So we are considering the fact that we have a magnetic field which is pointing into the page. Okay. And if I take into consideration, let's say, a positive charge, which is entering into the field, okay, the charge will experience a motion somewhat like this. Okay, so what is the underlying concept? That a moving charge, and if cutting the magnetic field, it has to experience magnetic force. Now, how to calculate the magnitude of this? So magnitude of force, so magnitude of this magnetic force is calculated by the formula F is equal to Q into V into D sine theta. Okay. Please understand this is applicable only for a moving charge case. Okay. Now, how do we find out the direction of this force? To find out the direction of this magnetic force, Okay, to find out the direction of this magnetic force, we use Fleming's left hand rule. Okay, in Fleming's left hand rule, the concept is again very straightforward. We have two sort of ways to remember it. Either we remember it as FPI, or at times students prefer remembering it as father, mother, and child. Okay, so what does first F represents? It's the thumb. Okay, B is basically the first finger of your left hand. I is the second finger of the left hand. Okay, so thumb here is representing direction of magnetic force. So F for force over here. So that's why father. Okay, the first finger represents the direction of magnetic field. Okay, that's why M. And the second finger represents the direction of positive charge. Okay, we also call this direction of positive charge as direction of current, that we will see shortly. Okay, so let's take some situation to understand in which direction will the force really act. So if we state the fact that magnetic field is going from left to right, okay, and we have a scenario where there is a positive charge which is going exactly perpendicular to the magnetic field at 90 degrees. Okay, so according to the Fleming's left hand rule, if I use the three fingers and keep it mutually perpendicular, and if I take out just the first finger, which is the direction of magnetic field, then I take out the second finger, which is indicating the direction of positive charge. So this is how the orientation is. So the first finger is pointing to the right, the second finger is pointing upwards, that's upwards on this paper on the screen. The moment I bring out thumb, I see that the magnetic force is going to act into the page, right? So the force is acting here into the page. And if I want to calculate its magnitude, I can calculate this by using F into V into B into sine theta. But what's theta equal to here? 90 degrees. So we calculate force as Q VB sine 90. 90 sine 90 is 1. So F equals to QVB. Okay. Now the same thing can be at an angle as well. Okay. So let's take one more scenario. And I want one of you to take the initiative to answer this question. So if I have a north pole and a south pole facing as follows, and if I have a positive charge entering the field, in which direction will the force act? Anyone who would like to try, please feel free to answer.
Down, right?
Pardon?
Down, right?
No. See, there are only three dimensions. Okay, अभी जो स्क्रीन आपको दिख रहा है उसके बाद एक लेफ्ट एक राइट है, अप और डाउन है. If you will see, the magnetic field is already pointing down because it's going from north to south. So force is definitely not downwards. Neither it is upwards. Neither it is right. Neither it is left. It has to be in the third dimension. That is into the screen or out of the screen. So start with your first finger, which is a field pointed downward, not to south. Okay. Then bring out a second finger, which is the direction of the positive charge. And if I see, this is how it is. So the answer is exactly the same thing again. If you see, it's again into the page. So the first finger, which is the field, is pointing down.
Your hand's a little out of camera. Can you bring it a little up?
Can you see it?
Yeah, yeah,
Yeah. So the magnetic field is pointing down.
yeah.
The second finger, which is the direction of current and positive charge, is pointing to the right.
Hmm.
So where is the force pointing, which is the thumb, into the screen?
Yeah.
Right. So again, here in this case, again, force was into the page.
So it is for reference. South pole of a magnet is positive charge or negative charge.
You will never treat poles as positive or negative charge, by the way. Okay. They have their magnetic field strength properties. Why are you taking it into consideration that it's positive or negative? This is not a scenario where a positive is repelling from south pole and attracting to the north pole. It is going into the page. So it's like if the charge was coming from the left and suddenly because it saw that there's a north and south pole field, it has changed its direction and gone into the screen. It's not going towards south. It's not going towards north. It's not kind of curving towards south. That's
Mm.
not called into the page. Are you understanding, Keshav?
Yeah, yeah.
Okay, this is a third dimension completely, right? Similarly, if I want to find out magnetic force on a current carrying conductor, okay. See, we need to understand here why is the magnetic force acting first and foremost, okay. If a magnetic material is there, only then a magnetic force is going to act on a material. Does that make sense? Can I get some acknowledgement from some of you listening?
Yes, sir.
So
Yeah,
what
sir.
happens here is when the charge is moving, when the charge has its speed, a moving charge produces a magnetic field around it. Okay. So the charge moving, okay, so moving charge produces a magnetic field around it. Okay. Now, due to this, what happens? There are two magnetic fields now, one of the charge itself and one of the magnet itself. Now, when these two magnetic fields interact, it creates a force of attraction or repulsion. And that is the reason why magnetic force comes into existence. Similarly, we know that when we talk about magnetic force on a current carrying conductor, in what direction does the magnetic field act on a current carrying conductor? Let's say if the current is carrying upwards, in what direction is the magnetic field going to be there? Yes,
Wait,
Siddharth.
sorry, what?
Out of the page.
So we have a current carrying conductor. Okay, so we have a current carrying conductor. And the principle states that a current carrying conductor produces a magnetic field around it. Okay, magnetic field around it. So if we have a conductor which is carrying current in the upward direction, in what direction will the magnetic field be? Jason said out of the page. Anyone else?
Yeah, so even I say it's out of the page.
Okay, you're saying out of the page. Okay, anyone else?
So it can either be out or in. Like, I don't know.
Okay, the correct answer to
Yeah,
this
I
is
think it's inside. I think it's inside.
the correct answer to this is the magnetic field will be in the anti-clockwise direction. Okay, how do I know that direction of magnetic field here? Direction of magnetic field. How do I find
Right
out?
hand rule it. Right hand rule it.
Right hand thumb rule. See, we haven't introduced the magnetic field for a current carrying wire externally yet. It is having its own magnetic field right now. And we do that using right hand thumb rule. What does the thumb rule state? That what does the thumb indicate? It is the direction of current. Are you guys able to recall knowledge?
Yes, sir.
So the curled fingers indicate what?
Direction of the let's say force or
Magnetic
magnetic
field.
field.
Direction of magnetic field. Are we clear? Right. So now if I hold this pen in my right hand such that the tip of the pen indicates the current flowing upwards. So my fingers are curling in the anti-clockwise direction. So we show this basically by drawing concentric circles here. So that as you move away from the wire, the spacing between the field lines increases, indicating that the field strength is decreasing. Okay. Now this is very tedious to draw. So we basically follow a convention which states that from the right hand side of the wire, the current is going into the page, but from the left hand side of the wire, from the right hand side of the wire, the magnetic field is going into the page, and from the left hand side, it is coming out of the page. So instead of drawing the concentric circles, I can draw these circles with a cross and circle with the dots. This is carrying current I. Are we clear? Now imagine if I have another wire here. Okay, that is also carrying current upwards. Will I get the same magnetic field pattern here as well? Okay. And because we have two different magnetic fields between the wires, we say that the wires experience a force of attraction because the magnetic field in between the wires are opposite direction. So we say that there is going to be attraction here. Okay. So in this case, if I want to find out what is the magnetic force on each other per unit length. Okay. So this magnetic force per unit length is calculated by the formula mu naught I1, I2, considering the fact that let's say the current was different upon 2 pi r. Now, I would like to still find out what is the magnitude of the magnetic field that the current is producing. So for that, I have to use one more formula. Okay. And to understand that, what we will consider is that consider a current carrying wire, a current carrying wire, a current carrying wire is placed in an external magnetic field. Okay. What does it mean? That if I have an external magnetic field due to the magnet, okay, here, 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 and here, and so on. Okay. And if I have a wire, okay, let's say this is a wire, and this wire is carrying current in this direction, such that the length of the wire exposed to the magnetic field is only of this length L. Okay, so here this is making an angle theta. So here we can calculate this force by using the formula BIL sine theta. Okay, now how did we come to this formula, or how did this formula get derived? So what do we know already? Okay, so we know that if the forces, so see, current carrying means there is flow of charge. Okay, and then when there's a flow of charge in presence of the magnetic field inside the conductor, okay, we know that F is equal to QVB sine theta. Okay, but can we write Q as current into time into V into B sine theta? Okay, why is that so? Since Q is equal to IT. And because the charge, which is the positive charge, which is in the direction of current, can travel a length L, a charge particle, which is a positive charge, can travel this length L inside the conductor, which is in presence of the magnetic field. We can write the speed into time as distance. This can be written as L into B into sine theta. Now, why is that so? Since time into speed is equal to distance, which is in this case as L. And that's how you get to this formula, which is BIL sine theta. Okay. Now look at this equation here. That is equation A and equation B. So from here, if I write F by L, I will get this as IB sine theta. And I can equate this equation with equation A. We can equate this with equation A to calculate B. Now the question here is that if I have I1 and I2, which current should I take here? That will be dependent on whom are you calculating the magnetic force. So if I say I want to calculate magnetic force on I1 due to I2, so then you will take I2 into consideration here. Okay, because I2 is producing a magnetic force out over there. Okay. Any questions so far? Guys, do you all have any questions?
The last part about I2 and I1, can you explain that again?
Yeah.
Like how you can.
Yeah. So I'm just going to write some things over here so that you guys can remember it. That if the question states, that calculate the value of B, okay, due to the force on I1 due to I2. Okay. Then you will say that force per unit length is equals to B times I2 sine theta. And you can equate this to mu naught I1 I2 upon 2 pi r. So then I2 and I2 will cancel out. Therefore, your B will be equal to mu naught I1 upon 2 pi r sine theta. If the conductor is at an angle, if the conductor is straight perpendicular to the field, then you'll just put sine theta as sine 90. Understood? But this is a very, very rare case that they generally ask you to correlate, these two equations. The questions are generally independent only because here we are talking about two forces. Similarly, you can use the same equation even for repulsion. The formula doesn't change. Okay. Are we clear till here? Any questions?
No, sir.
Okay. So
No, sir.
a quick question to all the standard level students first. Okay. That if I have a wire which is carrying current into the page, I have another wire which is carrying current out of the page. And if I have another wire which is carrying current into the page, this is wire A, this is wire B, this is wire C. Can you tell me the net direction of force on A due to B and C respectively?
So could you repeat the question? Sorry.
Yeah, the question is written as well over here. We want to find the net direction of force on A due to B and C respectively.
So A and B are into the page and C is out, right?
Yeah, yeah. The current is into the page and C is out of the page.
So will A and B attract?
Okay, so as we saw here that when the currents are in the same direction, they attract.
Hmm.
Okay, and we want to find it only on A. So we definitely know now that A will get attracted towards B. Let's call that force as F1.
And it will get repelled by C. A
It
will be repelled
will
by
get
C.
repelled by C. That let's say F2. So we can say that the net direction will be towards left, right?
Yeah.
Is everyone clear? This is how we find it out. Is that clear to everyone?
Yes, sir.
Okay. So common questions in MCQs, you'll find them a lot. Okay. Just taking you quickly through the syllabus guide for D3. So we've understood the motion of charged particle in uniform electric field, in magnetic field. Okay. How a motion of a charged particle perpendicular to uniform electric and magnetic field both is the last thing that we're going to do. And we have completed these 3 points here. Okay. So D3 as per standard level and higher levels is done with just one last concept where we are trying to understand if both the fields are present together, then what to do. Okay. So for both fields present together, both fields together. Okay. So for that, let's say we have a parallel plate here. Okay. The top end is positively charged. The bottom end is negatively charged. Okay. And we also have a magnetic field in between them, which is into the page. Okay. And now let's say if we want a negative charge particle here, okay, we want the negative charge particle. This is a charge particle which is stationary. So what are the different forces acting on this charge and in which directions?
So first will be the magnetic field. So it will go upwards.
Magnetic field.
Yeah, the magnetic force. Sorry.
Magnetic force due to electric field.
Yeah. Due to the plates.
That is electric field.
So is that not there in this?
तो मैग्नेटिक फोर्स बोल रहा है इलेक्ट्रिक फोर्स होगा कि मैग्नेटिक फोर्स होगा
Electric, sorry, electric.
Okay, so you have electric force acting upwards, understood? Which will be the other force? Yes, Nehal, Reed, Nandini. Come on, try. Guys, if it has to be one-way communication, that means you're not comprehending the information that is there. Do I have Nandini and Reet? Oh, they left, I think, in between. Yeah. Shaurya, would you like to try?
Sir, I'm not sure.
Okay. Siddharth?
So I'm just thinking.
So will another force be into the page?
See, we need to understand one thing. The charge is stationary means forces have to be balanced. That's a simple comprehension of it,
अच्छा.
right? ठीक
Then
है.
weight will be downwards.
एक इलेक्ट्रिक फोर्स है तो एक और फोर्स नीचे कुछ होना चाहिए जो इसको बैलेंस कर रहा है. वो कौन सा फोर्स हो सकता है?
Gravity.
Gravity. We cannot have a magnetic force here. Why? Because for magnetic force to be there, okay, the charge must be moving, right? What is the condition? That a moving charge experiences the magnetic force, right? But what is the condition I gave you a setup as? I told you the charge is stationary, correct? That means charge is not moving. Are we clear? So for this particular case, we can state that the electric force is equal to mg. That means EQ is equal to mg, which means V by D has to be V by D into Q has to be equal to mg. Done. That's your first case. Okay. In the second case, the question can ask you as follows, that we have a parallel plate here. Okay. The top end is, let's say, positively charged. The bottom end is, let's say, negatively charged. Okay. I have a positive charge here, and this positive charge is moving at a constant speed without any change in direction. Okay. Again, it means that forces must be balanced, which means the net force must be zero. Okay. What are the different forces if I just take the charge at this position that must be acting onto it? Tell me.
The magnetic and gravity, correct?
Okay. So let's say there's an electric force, which is, sorry, not electric, upwards. Electric force will act downwards. That is clear. Correct. Then there is mg also that is acting downwards. That is also clear. So then there has to be some force that is acting upwards. If I classify that force to be magnetic force, can you tell me in what direction will the magnetic field be pointing? देखो ये सब बहुत इंपॉर्टेंट केसेस है, ठीक है. कॉन्सेप्ट बड़ा सिंपल है, आपको याद रखना पड़ेगा क्योंकि आप भूल गए हो ये सारे कॉन्सेप्ट. We are very clear that there is a magnetic
Out of
field.
the page, right?
Magnetic field is present. So if my magnetic force, that is my thumb, has to point up, okay, and my second finger, which is indicating the direction of positive charge, if that is pointing to the right, so where is the magnetic field pointing?
Out of the page.
Into the page.
Up.
Keshav, left hand rule.
Oh, sorry, I was doing with the right hand.
इधर क्या पे? Positive charge is going to the right. The thumb is indicating that the force should act up. Okay. So the magnetic field has to act inwards. They can ask you to sketch this diagram. Okay. So now your equation becomes what? The magnetic force is equal to the weight force plus the electric force. Are we clear?
So just 1 second.
Yes. Process it. No problem. In the meanwhile, Siddharth, can you tell me what is the unit of magnetic field strength?
Tesla.
Okay. So units of B is Tesla. Okay. What about the magnetic force? Continue answering.
Newtons.
Newton. What about the current that we are referring here?
Amperes.
Okay. And what about the charge that we are using here?
Coulombs.
Coulombs. What about the length of the conductor?
Meters.
Meters. Okay. And what about the distance that we are using here between the plates?
Meters.
What about the potential difference we're using between the plates?
Volts.
Volts. Okay. Did we miss out on any other symbol that we've used and the unit has not been discussed? I think we've discussed for all the units, right? Okay. So these are all the units. Now, if you see in front of you, there are certain units written. What is one possibility that they can probably ask you under the criteria of MCQs where they just want to check your applications of units? Okay. So let's say if you want to find out the SI base unit of Tesla. Okay. So then what formulas we can use is that we have F equals to BIL. Okay. Sine theta would not have any unit, so we're not writing it. Now we want to make B the subject. So that will become F upon IL. Now F is Newton, current is ampere, length is meter. Now ampere and meter are already fundamental, but Newton we can write it as mass times acceleration, which means it is kg meters per second square, the whole divided by ampere into meter. So this cancels out. So we see that now 1 Tesla can be written as 1 kilogram, ampere raised to minus 1, S raised to minus 2. Are we clear? So it's important to basically, while you're practicing, observe that there are some different units, and they, if at all they are asking you to find it out into the SI base unit, then how you could do that. Okay, so Tesla is a unique unit here. Okay, so in regards to SL, that is it that we have.